The first type of line we'll deal with are secants. Now, a secant is a line which intersects a circle at exactly 2 points. So BF would be a secant. As you can see, it intersects at both C and D. Now, a secant segment is very closely related to a secant. In fact, it's part of a secant, but it reaches from a point outside the circle to the farthest intersection with the circle. So FC would be an example of a secant segment. By the way, BD would also be a secant segment because it reaches from a point outside the circle all the way to the farthest intersection on the circle, point D. The external part of a secant segment is the part that joins a point outside the circle to the first intersection of a circle. So FD would be an external part of a secant or of a secant segment. BC would also be an external part of a secant segment. What's the internal part of a secant segment? What would we call CD? Well, hopefully you remember that CD is just a chord. Okay, let's move on to tangents. Let's take a look at tangents. A tangent is a line that intersects a circle at exactly 1 point. So secant intersects at 2 points, a tangent just at 1. And that point of intersection is called the point of tangency. So there's really two terms there that I'd like you to make sure you get in your notes. Tangent and the point of tangency. Now, related to a tangent is a tangent segment. And that is the part of the tangent line between the point of contact, or I should say between a point outside the circle and the point of contact with the circle. That will be called the tangent segment. Okay, let's take a look then at two tangent postulates that come up and are very important, so make sure you get them in your notes. The first one tells us that a tangent line is perpendicular to the radius drawn to the point of contact. So this angle at T, if it meets a tangent, will always be 90 degrees. No matter where I move T, or if I manipulate the tangent using point P, well, that won't work, but the angle measure will always stay at 90 degrees. There's also another postulate that is the converse, that if a line is perpendicular to the radius at the point of contact, then that line must be tangent to the circle. Alright, so those are two important postulates, really kind of bread and butter for the second half of the chapter. But let's take a look at one more theorem that's going to come up a lot as well, and that's the two-tangent theorem. Two-tangent theorem tells us that if two tangents are drawn to a circle from an external point, then those two segments are congruent. So in other words, if I draw a tangent from Q to one point F, and I draw another tangent from Q to a point T, QF and QT are going to be congruent. Let's take a look at the proof of that. Well, we know that they're both tangent because that's given. And because they're tangent, they will meet the radii at 90 degrees. That's the postulate we just learned. We know OF and OT are congruent because they're radii of the same circle. So now let's draw QO, the line joining the center of the circle with the point outside the circle where the tangent segments begin. So now I know that QO is congruent to QO because of the reflexive property. So therefore these two triangles, QFO and QTO, are congruent by HL, which means of course that QF and QT, the segments, those sides are congruent by CPCTC. Alright, we're going to look at a couple more things with tangents. We're going to look at tangent circles and common tangent between two circles. The concept of tangent has a lot of applications. Let's first look at tangent circles. Tangent circles are two circles that only intersect at exactly 1 point. There are internally tangent circles like O and P because O is inside circle P. But there is also externally tangent circles because circle O is outside of circle P. Alright, let's take a look at what's called a common external tangent. Now, a common external tangent is a line or a segment tangent to two circles that does not cross the segment joining their centers. So in other words, KL is a common external tangent because the tangent does not pass between the two circles crossing the line which joins their centers. So common internal tangent, you can see that QR, the common external tangent, does cross the line joining the center of the two circles. So this will be a common internal tangent. The tangent runs between the two circles. Okay, let's look at something called the common tangent procedure for determining the length of the tangent if you know the radius or the distance between the centers of the circle. The common tangent procedures help us to find the length of a tangent between two circles if we know the radii and the distance between the centers. Or sometimes we can find the radii if we know the length of the tangent and the distance between the centers, or we can find the distance between the centers if we know the other two. You get the idea. Let's first take a look at the simpler of the two, which is the common external tangent. Now, you recall an external tangent does not cross the line connecting the centers of the two circles. It doesn't pass between them. So AB would be a common external tangent of circles O and P. The first thing we do every time for these types of problems is to draw the segment connecting their centers. Then we'll draw the radii to the points of contact. The next step is maybe the easiest one to overlook or to get wrong. And through the center of the smaller circle, in this case circle P, we'll draw a line parallel to the tangent. Now, many people draw it through the larger circle's center. Be careful, it's always through the smaller circle's center. Alright, then observe that that forms a rectangle, and we know it's a rectangle because we know that the angle formed by the radius and the tangent will be a right angle here and over here. And since these lines are parallel, angle OQP will be a right angle, so the right angle is always there. As I'll show you in a tutorial, we then have enough information to solve for this right triangle OQP, and we can find out whatever information we need from there. But be very careful. The right angle is always at the Q. There's a tendency to put it at the center of the larger circle. It's never there. It's always here at the intersection of the radius and this parallel line you've drawn. Okay, let's take a look at the common internal tangent then, because while it's the same steps, it comes off looking a little bit different. The common internal tangent does cross the line between the two centers of the circles. It does pass between them, so LM is a common internal tangent. Now you'll recognize the steps as being the same, but the figure that's created looks different. So KJ is going to be the line connecting the centers of the two circles, and then we draw the radii to the points of contact. Remembering, of course, that this is going to create right angles at the points of contact. I'll once again draw a line parallel to the tangent through the center of the smaller circle, in this case, point J. And then finally, we will form our right triangle and our rectangle, but notice that the rectangle is OJML, and that overlaps the right triangle, which will be OKJ. So the right triangle we're going to solve for is going to be this purple triangle, and unlike the last one, it overlaps the rectangle. Okay, I'll show you some examples of this in the tutorials. It is a little bit tricky, especially the second one. But you may want to rewind this video and watch it, but certainly pay attention to the tutorials. Okay, Ramblers, thanks for watching, and I hope this helped. Problem 3 on page 462 is an example problem which walks us through the common tangent procedure. They would like us to find the length of a common external tangent between these two circles, Q and P. Alright, let's walk through the steps. Now they tell us in the diagram that QA is 18 and that PB is 8. Those are the radii of the two circles. So step 1 tells us to draw a line connecting the two centers. Now notice, if the radii are 18 and 8, the length of this segment has to be 26. Then we will draw the radii to the points of contact. But those radii were already drawn in the picture, so we don't have to do step 2. Then, step 3 tells us through the center of the smaller circle, draw a line parallel to the common tangent. And this is the tricky step. It's got to be through the smaller circle, parallel to the common tangent. Now pay attention. Since this side is the radius of circle P is 8, that makes this portion of AQ 8. And not really drawn to scale very well, but this leg of the right triangle is 10. Now as I point out in the video, the right angle is going to be here. So I now have a right triangle that is QP, which I know is 26, and I know that this side is 10, and my right angle's there. So this final side of the right triangle has to be the third member of this 5, 12, 13 triangle. Since this is 2 times 5 and this is 2 times 13, hopefully you recognize this last side as 2 times 12, or 24. So the length of this side is 24 units, which, since this is a rectangle, makes AB equal to 24 units as well. Okay, thanks for watching, Ramblers. Problem 4 on page 463 is what we call a walk-around problem. And it tells us that this quadrilateral ABCD is tangent to the circle. That means at each point of contact here, the sides of the quadrilateral are tangent to the circle. Now, it's called a walk-around problem because it doesn't matter really where you start. You can just begin with one tangent and walk around. So they tell us the lengths of the sides. AB is 10, BC is 15, and CD is 18. I'm sorry, AD is 18. So they'd like us to find the length of CD. Well, let's start at this first tangent here and begin walking around. I'm going to call this first tangent X. Now, by the two-tangent theorem, it tells us that from a point outside a circle, if two tangents are drawn, like the tangent from B to E and B to F, those two tangents are congruent. So BF would also be X. Now, knowing that BC is 15, I know that FC must be 15 minus X, which makes this next tangent 15 minus X. Now, I don't know what CD is, so maybe I have to come back to this side over on the left, AB, and recognize that if BE is X, then AE has to be 10 minus X. So that makes this tangent also 10 minus X, and this becomes 18 minus the quantity 10 minus X, which simplifies to 8 plus X. So this is also 8 plus X, giving us a length of CD equaling 8 plus X plus 15 minus X. Now you'll notice that the two X's cancel out, leaving us that CD equals 23. It's almost like magic how these work every time, but the trick is to label carefully. Don't get too confused where you start getting these nests of parentheses like down in this corner, and just work your way around the quadrilateral. Okay, Ramblers, good luck. Okay, in this example, we're going to look at the length of a common internal tangent. Given that the radii of circle O is 8, the radius of circle P is 4, and the distance between the circles is 3. Now, be careful with that distance between the circles, because literally that is from where one circle ends to the next circle. It is not the distance between the centers. If we look for the distance between the centers, it will be said explicitly. when we talk about the circles, remember, we're talking about that ring of points, not the center of the circle. Okay, so let's go through the common tangent procedure outlined on page 462. Step 1 said to draw the segment joining the centers. So I'm going to go ahead and draw OP, recognizing that the radius of circle O is 8, the radius of circle P is 4, and the distance between the centers is 3. So that's going to add up to a total of 15. Alright, now step 2 tells me to draw the radii to the points of contact. So there's one and there's the other. And I usually take this moment to mark the lengths of the radii. So we have already marked that circle P's radius is 4, and we know that circle O's is 8. The next step tells us through the center of the smaller circle, which in this case is circle P, draw a line parallel to the tangent and extend the radius of the larger circle if need be. Well, we definitely need to. So I now recognize that since the radius of circle P is 4, that becomes the side of a rectangle, and so this extension of the radius of circle O is also going to be 4, giving me an entire length of this side of my now developing triangle as 12. So I'm going to mark this point up here just to give it a name. I'm going to call it point Q. So if I draw my triangle below, I now have my extension of radius of circle O to make a length of this side of 12, and then I am looking for PQ. Why am I looking for that? Well, notice that PQ, that line parallel through the center, is going to be the same as the length of my common internal tangent. So hopefully you recognize that this is a 9, 12, 15 triangle. So the length of the tangent is 9. Okay, Ramblers, you'll get some examples like this in the exercises. I hope this helps.